Welcome to For Science Salah Lotfy channel, where we bring you closer to groundbreaking research and the scientists behind it. Today we spotlight a prominent figure in atomic and plasma physics, Professor Dr. Gaber Omar, whose contributions have left a lasting impact on scientific progress. Professor Dr. Gaber Omar is a distinguished physicist from the Physics Department, Faculty of Science, Ain Shams University, Egypt. He is widely recognized for his pioneering research in atomic physics and his role in advancing theoretical models that explain complex atomic and plasma phenomena. Dr. Omar's research spans multiple scientific directions, including 1. Dielectronic recombination in plasma, exploring how excitation states influence energy distributions in plasma, with applications in plasma physics and radiation control. 2. Electron shake-off phenomenon, investigating how sudden changes in nuclear charge affect orbital electrons, reshaping our understanding of atomic rearrangements. 3. Hollow ions, studying the production and interactions of hollow ions to understand high-energy particle collisions with atoms. 4. Strong electron capture, delving into unusual electron capture phenomena, especially in heavy atoms, to uncover new atomic behaviors. 5. Theoretical models of atomic interactions, developing mathematical frameworks to explain experimental phenomena in atomic and molecular physics. Dr. Omar's career reflects a remarkable evolution of scientific focus. In the 1980s, his work centered on dielectronic recombination in heavy ions, such as calcium and molybdenum, using K and L shell excitation. The 1990s marked a shift to studying the electron shake-off effect caused by nuclear charge changes and the production of hollow ions in plasma collisions. From 2000 to 2007, he applied his findings to plasma physics, investigating how excited states impact energy distributions and advancing theoretical models to maturity. Dr. Omar's research has significantly impacted various fields, from plasma physics and laser technologies to nuclear interactions and radiation applications. His studies on atomic interactions provide critical insights for industries. From laser machining to medical radiation therapy, Dr. Omar's legacy remains a cornerstone for scientists and engineers alike. Professor Dr. Gaber Omar's contributions remind us of the transformative power of science. To learn more about groundbreaking research, stay tuned to For Science Salah Lotfy channel. Thank you for watching. A tiny universe rocked. Imagine an atom's heart suddenly changing. Atoms are often depicted as miniature solar systems. Electrons, like planets, orbit a central nucleus. But unlike our solar system, the atom's heart, its nucleus, can undergo dramatic changes. When the number of protons in the nucleus suddenly shifts, the delicate balance of the atom is thrown into disarray. Imagine the sun suddenly becoming more massive. Planets, once comfortably in orbit, would be thrown into new trajectories, some even ejected from the system entirely. This is akin to what happens within an atom when its nucleus experiences a sudden change in charge. This change can occur through various processes, such as radioactive decay. Specifically, a type of decay called electron capture can cause this atomic upheaval. In electron capture, the nucleus absorbs an electron, transforming a proton into a neutron. The result? The atom's nuclear charge decreases by 1, sending shockwaves through the surrounding electron cloud. This sudden shift in the balance of forces within the atom is what leads to a fascinating phenomenon known as electron shake-off. Shaken from their path, how sudden shifts eject electrons. Electron shake-off is a consequence of the quantum world's inherent uncertainty. When the nucleus changes charge abruptly, the electrons are caught off guard. They are no longer in the right energy levels for the new nuclear landscape. Think of it like a sudden earthquake shaking a building. Some objects might simply vibrate, while others are completely dislodged. Similarly, some electrons in the atom will simply shift to different energy levels, adapting to the new nuclear environment. However, other electrons are not so lucky. The sudden change is so drastic that they are completely ejected from the atom, like books flying off a shaking shelf. These ejected electrons are what we call shake-off electrons. The shake-off process is not just a theoretical curiosity, it has real-world implications, particularly in fields like plasma physics and nuclear medicine. Understanding and predicting electron shake-off is crucial for interpreting data from these areas and for developing new technologies. Cascading chaos. One vacancy leads to a scramble for stability. The ejection of an electron, especially from the innermost shell, the K shell, leaves a void in the atom. Nature abhors a vacuum, and so begins a cascade of events as the atom strives to regain stability. Imagine a line of people, each holding the one behind. If the first person suddenly disappears, the others will stumble forward, each trying to regain their balance. In an atom, electrons from higher energy levels will drop down to fill the vacancy in the K-shell. This transition isn't a smooth, energy-neutral process. As electrons shift to lower energy levels, they release energy in the form of X-rays. These X-rays carry a signature unique to the atom from which they originate, much like a fingerprint. This cascade of electron rearrangement and X-ray emission is crucial in many applications, from materials analysis to medical imaging. By detecting and analyzing the emitted X-rays, scientists can identify the elements present in a sample or even diagnose diseases. Section 4. From Atoms to Application. Shake-off's role in technology and medicine. The seemingly esoteric phenomenon of electron shake-off has surprisingly tangible applications in our technological world. Take, for instance, the realm of nanotechnology. As we manipulate materials at the atomic level, understanding how electron configurations change under stress becomes crucial. Shake-off can alter the properties of nanomaterials, and harnessing this effect could lead to novel materials with tailored properties. In medicine, radioactive isotopes that undergo electron capture are used in imaging and therapy. For instance, iodine-123, which decays by electron capture, is used in thyroid imaging. The emitted X-rays from the electron rearrangement process allow doctors to visualize the thyroid gland and diagnose any abnormalities. Furthermore, the shake-off electrons themselves can be used in cancer therapy. These electrons, carrying kinetic energy from the nuclear transformation, can damage DNA in tumor cells, leading to their destruction. Section 5. Beyond the basics. What this means for energy and the universe's secrets. Beyond its practical applications, electron shake-off holds profound implications for our understanding of the universe. In the heart of stars, nuclear reactions are the engines of energy production. Electron capture, a key player in shake-off, plays a crucial role in these stellar furnaces, influencing the rate of nuclear burning and the elements forged within. Astrophysicists studying distant stars rely on understanding these atomic processes to decipher the cosmos's chemical evolution. In the realm of fusion energy research, replicating the sun's power on Earth hinges on our ability to control and manipulate plasmas, superheated gases where atoms have been stripped of their electrons. Electron shake-off influences the behavior of these plasmas, and understanding this phenomenon is vital for achieving stable and sustainable fusion reactions. Atoms are the building blocks of our universe. They are the fundamental units that make up everything we see, touch, and even breathe. Without atoms, the universe as we know it would not exist. They are tiny, teeming with energy, and always in motion. These particles are constantly moving, interacting, and creating the very fabric of our reality. Imagine a nucleus, the atom's heart, orbited by electrons, the atom's restless dancers. These electrons move in specific patterns, creating a delicate balance within the atom. These electrons are not just randomly scattered. They follow defined paths known as orbitals, which are determined by the atom's energy levels. They are bound to the nucleus by electromagnetic forces. These forces are incredibly strong, holding the atom together and giving it its structure. These forces dictate their movements, their energy levels, and ultimately the atom's chemical behavior. The way electrons move and interact determines how atoms bond and react with each other. Understanding how electrons behave within an atom is crucial. It helps scientists predict and explain the properties of different materials and elements. It unlocks the secrets of chemical reactions. By studying these interactions, we can develop new materials and technologies. It explains how light interacts with matter. This understanding is essential for developing optical technologies and understanding the behavior of light in different environments. It even allows us to develop technologies like lasers and semiconductors. These innovations have revolutionized industries and changed the way we live. But what happens when this delicate balance within the atom is disrupted? When the forces holding the atom together are altered, the atom can change in fundamental ways. What happens when the nucleus itself undergoes a transformation? This can lead to significant changes in the atom's properties and behavior. That's where the phenomenon of electron shake-off comes into play. This process occurs when an electron is ejected from the atom, often due to high-energy interactions. It's a fascinating process that provides a glimpse into the dynamic world of atomic interactions. By observing electron shakeoff, scientists can learn more about the forces at play within the atom. By studying electron shakeoff, we gain a deeper understanding of the universe's fundamental forces. This knowledge can lead to new discoveries and advancements in science and technology. Imagine a sudden jolt in the very heart of an atom. This isn't just any ordinary jolt, it's a profound disturbance that can alter the very nature of the atom itself. This is what happens during events like beta decay, a process that fundamentally changes the atomic structure. In beta decay, a neutron in the nucleus transforms into a proton, spitting out an electron and an antineutrino. This transformation is a key aspect of radioactive decay. This sudden change in the nucleus's charge is like a seismic shift for the orbiting electrons. The entire atomic structure feels the impact. This shakeup can cause an electron to be ejected from the atom, like a dancer flung off a rapidly spinning carousel. The energy transfer is immense. This ejected electron is what we call a shake-off electron. It's a fascinating phenomenon that reveals much about atomic interactions. The process is aptly named as the electron is essentially shaken loose from its atomic bonds. This breakage is a critical event in atomic physics. Electron shake-off isn't limited to beta decay. It can occur in various other atomic processes. It can also occur during other processes that perturb the atomic core, such as photoionization. This is another way atoms can be disturbed. In photoionization, a high-energy photon, like an X-ray, strikes an atom and transfers its energy to an electron, ejecting it. This interaction is crucial in many scientific fields. This too can create a vacancy leading to the shake-off of another electron. The chain reaction of events is fascinating to observe. Electron shakeoff might sound like a rare and esoteric phenomenon, however, it occurs more frequently than one might think. However, its effects are far-reaching. The implications of this process extend into various scientific disciplines. It impacts fields ranging from astrophysics to medicine. Understanding this phenomenon can lead to breakthroughs in these areas. Understanding how often this shakeoff occurs and what energies the ejected electrons carry is vital in these fields. This knowledge helps scientists make accurate predictions and develop new technologies. Predicting electron shakeoff is a complex task. It requires sophisticated theoretical models that take into account the quantum nature of electrons. These models must factor in the intricate dance of forces between the electrons and the nucleus. One widely used theoretical framework is the sudden approximation. This approximation assumes that the change in the nucleus happens instantaneously relative to the electron's response time. While this simplifies the calculation, it still provides valuable insights into the shakeoff process. These models help us calculate the probability of electron shakeoff occurring for different atoms and under various conditions. They also allow us to predict the energy distribution of the ejected electrons. These predictions are crucial for interpreting experimental data and for understanding the implications of electron shakeoff in different contexts. To put these theoretical models to the test, researchers often focus on relatively simple atoms like neon and argon. These atoms provide a good testing ground because their electronic structure is well understood. Extensive research has been conducted on electron shakeoff in neon and argon. These studies have revealed intriguing details about the process. For instance, the probability of electron shakeoff occurring is higher for inner shell electrons, those closer to the nucleus. This is because they experience a more dramatic change in the nuclear charge during the shakeup. Furthermore, the energy distribution of the ejected electrons is not random. It follows specific patterns that are characteristic of the atom and the process that triggered the shakeoff. These patterns provide valuable fingerprints for identifying electron shakeoff events in experimental data. Section 5. Theory meets reality. Bridging the gap between predictions and experiments. While theoretical models provide a framework for understanding electron shakeoff, experimental validation is crucial. Over the years, sophisticated experiments have been designed to measure electron shakeoff probabilities and energy distributions. One such technique involves bombarding atoms with X-rays and precisely measuring the energy of the ejected electrons. By analyzing this data, researchers can determine the contribution from electron shakeoff events. Comparing these experimental results with theoretical predictions reveals a complex picture. While the models generally capture the overall trends, some discrepancies exist. These discrepancies highlight the limitations of current theoretical approaches and motivate the development of more refined models. Section 6. From Atoms to Applications, the real-world impact of electron shakeoff research. Electron shakeoff might seem like a phenomenon confined to the realm of atomic physics, but its implications are far more widespread. This seemingly small event can have a ripple effect across various scientific disciplines. Understanding this process is crucial in various fields, from medical physics to material sciences, and even astrophysics. In medical physics, for instance, in radiation therapy used to treat cancer, understanding electron shakeoff helps in accurately modeling the dose deposition in the body. This precision is vital for targeting cancer cells while sparing healthy tissue. This leads to more effective treatments with fewer side effects, improving patient outcomes and quality of life. In material sciences, electron shakeoff plays a role in the interaction of radiation with materials. This understanding is essential for developing new materials that can withstand high levels of radiation. This knowledge is crucial for developing radiation-resistant materials used in nuclear reactors and space exploration. These materials ensure the safety and longevity of equipment in extreme environments. And in astrophysics, electron shakeoff contributes to the X-ray spectra observed from celestial objects like black holes and neutron stars. These X-ray emissions provide a window into the extreme conditions present in these distant objects. By studying these spectra, astrophysicists can glean information about these extreme environments, helping us understand the universe better. These are just a few examples of how understanding a seemingly esoteric atomic process like electron shakeoff has tangible, real-world implications. The research in this field continues to unlock new possibilities and applications across various scientific domains. Section 7. Journey to the Future. Electron shakeoff and the quest for new technologies. As we delve deeper into the subatomic world, our understanding of electron shakeoff continues to evolve. This knowledge paves the way for new technologies and innovations. For instance, researchers are exploring ways to harness the energy released during electron shakeoff. This energy could potentially be used to develop novel energy sources. Imagine a world powered by the very atoms that make up everything around us. Furthermore, a deeper understanding of electron shakeoff could lead to more precise and efficient radiation therapies. Imagine targeting cancer cells with pinpoint accuracy, minimizing damage to healthy tissue. These are just a few examples of the exciting possibilities that lie ahead. Section 8. Electron shakeoff in space, unraveling the cosmos. One atom at a time. Looking beyond our planet, electron shakeoff plays a crucial role in shaping our understanding of the cosmos. Astrophysicists study the X-ray emissions from distant celestial objects. These emissions often carry the signatures of electron shakeoff events, providing valuable clues about the composition, temperature, and processes occurring in these objects. For instance, by analyzing the X-ray spectra from black holes, scientists can infer the properties of the matter being pulled in. This helps us understand the extreme gravitational forces at play near these cosmic behemoths. Similarly, studying electron shakeoff in the context of supernova explosions sheds light on the processes that lead to the creation of heavy elements. These elements, the building blocks of planets and life itself, are forged in these cosmic furnaces. Section 9. Conclusion. The enduring allure of the subatomic world. The study of electron shakeoff exemplifies the beauty and complexity of the subatomic world. What seems like a minuscule event within an atom ripples outward, impacting fields as diverse as medicine, astrophysics, and energy production. As we continue to refine our theoretical models and develop more sophisticated experimental techniques, we gain a deeper appreciation for the intricate dance of particles that governs our universe. The journey into the heart of the atom is far from over. Each new discovery opens up new avenues of exploration, pushing the boundaries of human knowledge and leading us to a brighter. Imagine an atom as a bustling city, teeming with activity and energy. At its heart lies the nucleus, a dense and energetic core, much like the city center where all the major activities converge. Buzzing around this nucleus are the electrons, inhabiting specific energy levels like orbital highways, each with its own unique path and speed. These electrons are in constant motion, engaged in an intricate dance governed by the laws of quantum mechanics. They move so fast and unpredictably that their exact positions are often a mystery, only describable by probabilities. Now picture a sudden change in the nucleus, like a cosmic earthquake. This could be due to a variety of reasons, such as a collision with another particle or a sudden release of energy. This disruption can jolt the entire atomic city, sending ripples through the electron highways. The electrons, sensitive to these changes, react almost instantaneously. Some electrons might find their energy levels shifted, moving to a higher or lower orbital as they absorb or release energy, while others could be ejected entirely from the atom, a process known as ionization. This can happen when the energy imparted to the electron is so great that it overcomes the attractive force of the nucleus. This phenomenon, known as electron shake-off, offers a fascinating glimpse into the dynamic interplay between the nucleus and its surrounding electrons. It shows how interconnected and sensitive the atomic structure is to changes. By studying electron shake-off, we can unravel the secrets of atomic insights into the fundamental forces that shape our universe. This research not only helps us understand the building blocks of matter, but also paves the way for advancements in technology, medicine, and energy. Scientists around the world are delving into these mysteries, using cutting-edge technology to observe and manipulate these tiny particles. Their work is crucial in developing new materials, improving medical treatments, and even in the quest for sustainable energy solutions. The dance of electrons is not just a theoretical concept, it has real-world applications that impact our daily lives. From the screens we use to the medicines we take, understanding electron behavior is key to innovation. As we continue to explore the invisible dance of electrons, we unlock new possibilities and deepen our understanding of the universe. Each discovery brings us one step closer to mastering the fundamental forces that govern all matter. The journey of discovery is ongoing, and the potential is limitless. The invisible dance of electrons is a testament to the beauty and complexity of the natural world, and our quest to understand it is a never-ending adventure. Imagine a game of musical chairs played on an atomic scale. In this microscopic version of the game, the players are not children but subatomic particles, specifically electrons, and the chairs are the energy levels within an atom. Just like in the traditional game, the music represents the stability of the atomic nucleus. When the music stops, or in this case, when the nucleus undergoes a sudden transformation, the electrons must quickly find new positions to maintain the atom's stability. The nucleus undergoes a sudden transformation, like a chair being removed from the circle. This transformation can be triggered by various processes, such as radioactive decay or interactions with high-energy photons. When this happens, the electrons, which were previously in a stable configuration, are suddenly thrown into disarray. They must quickly adjust to the new configuration of the nucleus, much like players scrambling for a chair when the music stops. The electrons, caught off guard, scramble to find new energy levels to occupy. This process is not just a simple game, it involves complex quantum mechanics. Electrons exist in specific energy levels or orbitals around the nucleus, and when the nucleus changes, the energy levels can shift. The electrons must then transition to these new levels, which can involve absorbing or releasing energy in the form of photons. This rapid adjustment is crucial for the stability of the atom. This analogy captures the essence of electron shake-off. Electron shake-off is a phenomenon where electrons are ejected from an atom due to sudden changes in the nucleus. This can happen during processes like beta decay or photoionization. The sudden change in the nucleus creates a ripple effect, causing the electrons to be shaken off from their original positions. This is a critical concept in understanding atomic behavior and the interactions between subatomic particles. When the nucleus undergoes a rapid change in charge, such as during beta decay or photoionization, the electrons are forced to readjust their positions. Beta decay is a type of radioactive decay where a neutron in the nucleus is transformed into a proton, emitting an electron and an anti-neutrino in the process. This transformation changes the charge of the nucleus, which in turn affects the surrounding electrons. They must quickly find new energy levels to occupy, leading to the phenomenon of electron shake-off. This rearrangement can result in an electron being ejected from the atom, leaving behind a positively charged ion. The ejected electron can carry away a significant amount of energy, and the remaining ion is left in an excited state. This process is not only fascinating, but also has practical implications in fields like radiation therapy and astrophysics. Understanding how electrons are ejected and how ions are formed helps scientists develop better technologies and treatments. Beta decay, a type of radioactive decay, involves the transformation of a neutron into a proton within the nucleus. This process is accompanied by the emission of an electron and an antineutrino. The change from a neutron to a proton increases the positive charge of the nucleus, which has a profound effect on the surrounding electrons. They must quickly adjust to this new charge distribution, often resulting in the ejection of one or more electrons from the atom. This change alters the nuclear charge, creating a domino effect that can lead to electron shakeoff. The sudden increase in positive charge within the nucleus causes a shift in the energy levels of the electrons. This shift can be so significant that some electrons are no longer bound to the atom and are ejected. This domino effect is a key aspect of understanding how atomic and subatomic particles interact and how energy is transferred within an atom. Photoionization, on the other hand, occurs when a high-energy photon, like an X-ray, strikes an atom and knocks an electron loose. This process is different from beta decay, but can also result in electron shakeoff. When a high-energy photon interacts with an atom, it can transfer enough energy to an electron to overcome the binding energy that holds the electron in place. This results in the ejection of the electron and the formation of a positively charged ion. This sudden removal of an electron can also trigger shakeoff in other electrons. When one electron is ejected, the remaining electrons must quickly readjust to the new charge distribution within the atom. This can cause a cascade effect, where multiple electrons are ejected in quick succession. This phenomenon is not only a fascinating aspect of atomic physics, but also has practical applications in fields like material science and radiation therapy. Understanding electron shakeoff helps scientists develop better models of atomic behavior and improve technologies that rely on precise control of atomic and subatomic particles. Predicting the likelihood of electron shakeoff is a complex task that requires sophisticated theoretical models. One such approach is the Hart-Fock method, a powerful computational tool used to approximate the behavior of many electron systems. The Hart-Fock method treats each electron as if it moves in an average field created by the nucleus and all other electrons. This simplification allows us to calculate the wave functions of individual electrons, which describe their probability distributions within the atom. By comparing the wave functions before and after the nuclear transformation, we can estimate the probability of an electron being shaken off. These calculations provide valuable insights into the factors that influence shakeoff, such as the energy of the ejected electron and the atomic number of the element. Section 4. The Auger correction fine-tuning the atomic orchestra. While the Hart-Fock method provides a good starting point, it doesn't capture all the nuances of electron shakeoff. The Hart-Fock method is a fundamental approach in quantum chemistry and physics, used to approximate the behavior of electrons in atoms and molecules. However, it simplifies the complex interactions between electrons, treating them as if they move independently in an average field created by all other electrons. This approximation, while useful, misses out on some critical details, especially when it comes to the phenomenon known as electron shakeoff. One important refinement is the inclusion of the Auger correction, which accounts for the interaction between the ejected electron and the remaining electrons in the atom. The Auger correction is named after the French physicist Pierre Auger, who discovered the effect in the 1920s. This correction is crucial because it considers the dynamic response of the remaining electrons when one electron is ejected from the atom. Without this correction, our models would be incomplete, failing to accurately predict the behavior of the atom after ionization. Imagine the ejected electron as a departing musician leaving an orchestra. In an orchestra, each musician plays a specific role, contributing to the harmony of the entire ensemble. When one musician leaves, the remaining musicians must adjust their positions and roles to maintain the balance and harmony of the performance. This analogy helps us understand the complex rearrangement that occurs within an atom when an electron is ejected. Its departure creates a void that other musicians try to fill, leading to a rearrangement of the entire ensemble. Similarly, in an atom, the ejection of an electron creates a vacancy that the remaining electrons must fill. This leads to a reorganization of the electron cloud, with electrons shifting to new positions and energy levels to restore stability to the atom. This process is not instantaneous. It involves complex interactions and energy exchanges among the electrons. Similarly, the Auger effect describes how the ejection of one electron can influence the energy levels and behavior of other electrons in the atom. The Auger effect is a two-step process. First, an electron is ejected from an inner shell of the atom, creating a vacancy. Then, an electron from a higher energy level falls into the vacancy, releasing energy. This energy can be transferred to another electron, causing it to be ejected from the atom. This cascading effect can significantly alter the energy distribution and behavior of the remaining electrons. Incorporating the Auger correction into our calculations is crucial for accurately predicting the final state of the ionized atom. By including this correction, we can better understand the energy levels and configurations of the electrons after ionization. This is essential for many applications, including spectroscopy, where precise knowledge of electron behavior is needed to interpret experimental data. It also plays a vital role in fields like materials, science, and nanotechnology, where the properties of materials are often determined by the behavior of their electrons. It helps us determine not only the probability of electron shakeoff, but also the specific energy levels of the remaining electrons. Understanding these probabilities and energy levels allows scientists to make more accurate predictions about the behavior of atoms and molecules under various conditions. This knowledge is crucial for designing new materials, developing advanced technologies, and exploring fundamental questions in physics and chemistry. The Auger correction, therefore, is a key tool in the ongoing quest to fine-tune our understanding of the atomic orchestra. Section 5. Neon and Argon, a tale of two atoms. To test the accuracy of our theoretical models, we can compare them to experimental measurements of electron shakeoff. Neon and argon, two noble gases with relatively simple atomic structures, have served as valuable testbeds for these studies. Experiments involving the radioactive decay of isotopes like neon-19 and argon-37 have provided precise data on the probabilities of electron shakeoff in these atoms. These measurements have allowed us to fine-tune our theoretical models and gain a deeper understanding of the factors that influence shakeoff. For instance, experiments have shown that the probability of shakeoff increases with the atomic number of the element. This trend reflects the fact that larger atoms have more electrons, making them more susceptible to disruptions caused by nuclear transformations. Have you ever wondered how atoms become ions? It's a fundamental process in physics, and it's happening all around us. One intriguing mechanism is the electron SKOF process. SKOF stands for shake-off following electron capture. It's a fascinating phenomenon that influences how atoms lose or gain electrons. Let's delve into this world and explore its implications. Imagine an atom as a miniature solar system. The nucleus sits at the center, like our sun. Electrons orbit the nucleus, like planets. Now imagine a disturbance in this system. That's where electron SKOF comes in. It disrupts the delicate balance, causing changes in the atom's charge. Electron SKOF is particularly relevant in ionization. This is the process where an atom gains or loses electrons, becoming an ion. Understanding this process is crucial in many fields, from astrophysics to materials science. Let's take two common elements, neon and argon. These noble gases are known for their stability. However, even these stable atoms can be ionized. Electron SKOF plays a role in this process. Neon, with its 10 electrons, is relatively small. Argon, with 18 electrons, is larger. This difference in size affects how electron SKOF impacts their ionization. The larger argon atom is more susceptible to electron shakeoff. Think of it like this. A disturbance in a small pond has a localized effect. A disturbance in a large lake creates ripples that spread farther. Similarly, electron SKOF has a more pronounced effect on argon's ionization compared to neon. This difference is crucial in understanding how these elements behave in various environments. For example, in a plasma, where atoms are constantly ionized and recombined, the role of electron SKOF becomes significant. Beta decay is a type of radioactive decay. It's a process where a neutron in an atom's nucleus transforms into a proton, releasing an electron and a neutrino. This process also triggers electron SKOF. The ejected electron can interact with other electrons in the atom, causing them to shake off as well. In neon, beta decay and the subsequent electron SKOF might only eject a few electrons. But in argon, the effect is amplified. More electrons are shaken off due to the larger atom size and the higher number of electrons available. This difference in ionization behavior during beta decay is critical in many areas. For instance, in radioactive dating, understanding the precise ionization pathways is crucial for accurate measurements. Section 4. Photoionization. Light's role in ionization. Light can also ionize atoms. This process, called photoionization, occurs when a photon with enough energy interacts with an atom, ejecting an electron. And guess what? Electron SKOF plays a role here too. When a photon knocks out an electron, it can create a vacancy in the atom. This vacancy can trigger a cascade of events, leading to more electrons being shaken off. Again, this effect is more pronounced in argon than in neon. Photoionization is a fundamental process in astrophysics. It's how stars ionize the gas and dust around them, creating beautiful nebulae. Understanding the contribution of electron SKOF in photoionization helps us to paint a more complete picture of these stellar nurseries. Section 5. Beyond traditional models. The importance of electron SKOF. For years, scientists have used traditional models to understand ionization, but these models often fall short. They don't fully account for the subtle yet significant effects of electron SKOF. By incorporating electron SKOF into our models, we gain a more accurate and nuanced understanding of ionization processes. This is particularly important in fields where precision is key, such as in the development of next-generation particle detectors or in the study of radiation interactions in biological systems. The discovery and characterization of electron SKOF highlight the ever-evolving nature of science. As we delve deeper into the quantum world, we continue to uncover new and fascinating phenomena that challenge our understanding and push the boundaries of knowledge. This pursuit of knowledge is what drives scientific exploration and leads to groundbreaking discoveries that shape our world.
Welcome to For Science Salah Lotfy channel. Today we pause to honor the life and legacy of a remarkable scientist, Professor Dr. Gaber Omar, whose contributions to the field of atomic and plasma physics have left an indelible mark on the scientific community in Egypt and beyond. Born in 1953, Professor Dr. Gaber Omar dedicated his life to advancing the frontiers of knowledge. As a distinguished member of the physics department at Ain Shams University, he inspired countless students and colleagues with his groundbreaking research and unwavering commitment to science. Sadly, the world lost this brilliant mind in 2007, but his work continues to resonate with the global scientific community. Dr. Gaber Omar's research in atomic physics, particularly his studies on electron shake-off processes and ionization dynamics, has been a cornerstone for many advancements in the field. His contributions have paved the way for innovative applications in energy, medicine, and technology, enriching the scientific discourse in Egypt and across the world. On behalf of his students, colleagues, and the global scientific community, For Science Salah Lotfy channel extends heartfelt gratitude to Professor Dr. Gaber Omar. His teachings and mentorship have shaped the careers of many, while his research has provided invaluable insights for scholars worldwide. His name will forever be etched in the annals of science as a beacon of knowledge and dedication. To the family of Professor Dr. Gaber Omar, we express our deepest respect and appreciation. His contributions to science are a testament to his passion and brilliance. As his legacy continues to inspire, we honor him not only as a scientist, but as a cherished individual who has touched the lives of many. Today we celebrate the life of Professor Dr. Gaber Omar and his immeasurable contributions to the scientific world. From his students and colleagues to the recipients of his research in Egypt and around the globe, we say, thank you, your legacy will never be forgotten. This is For Science Salah Lotfy channel. Thank you for joining us in this tribute.